Learning Outcome 4.4. Apply partial fractions to finding inverse Fourier transforms. Similar to Learning Outcome 4.2 and Learning Outcome 4.3, we want to find the inverse Fourier transform given an equation. Here in the examples for this learning outcome, our Fourier transform is a ratio of polynomials in terms of j omega. For example, we want to use partial fractions to put our x to j omega into the form in the sum of smaller ratios of polynomials. Let's take an example. We can take our x to j omega, convert it into partial fractions, and then we can use table 4.2, property 13, together with linearity property, to invert it, just using the tables, and we wind up with a sum of two different exponentials. Remember that u of t is very important and the answer is incorrect without it. If you don't remember how to do partial fractions, there's a handout on partial fractions on Blackboard, and there's a video reviewing partial fractions on Blackboard. Another example. Here we have repeated roots. When we use partial fractions, we still get two terms, but one which is squared, one which is not. Therefore, in addition to property 13 from table 4.2, we also have to use property 14. Property 14 has the squared term in the denominator, which gives us a t in our inverse transform. That gives us the result of this x of t. Here's another example. Here we have an improper ratio of polynomials in our fraction. Whenever this occurs, it means the order of the numerator is equal to or greater than the order of the denominator in our fraction. When this occurs, we need to first use long division to create a constant term if the two fractions have the same order, or this will be a polynomial term if the order of the numerator is greater than the order of the denominator. That will give us a proper fraction here. On this proper fraction, we again use partial fractions. On this constant term, we use property 10 from table 4.2, which says that the inverse transform of a constant is delta of t. On these other two terms, we continue to use property 13 from table 4.2, and we get the result as shown here.